welcome to Virtual Protocol Podcast.
For the last couple of years, interacting with AI has felt a bit like, well, like talking to a brilliant entity that's just trapped inside a glowing rectangle.
Right, yeah, like a brain in a jar.
Exactly. A brain in a jar, you type a prompt, the screen spits out text, and that is just the absolute boundary of the relationship.
It's a completely sterile environment. I mean,
Right.
the intelligence lives entirely in this realm of, language and code and pixels. It's utterly detached from the actual physical reality we live in.
But imagine taking that brain in the jar and suddenly giving it a highly sensitive pair of hands and then just tossing it into a chaotic, messy kitchen.
Spilling liquids, fragile eggs, tangled wires, all of it.
Yeah, exactly. And that is the exact threshold we are crossing right now. So welcome to the deep dive. The world of AI never sleeps, as you know, but we've got an absolute avalanche of breakthroughs to talk about today.
We really do.
And our mission here is to cut through all the overwhelming noise of these new tech releases just to reveal this massive paradigm shift. Because AI is breaking out into the messy physical world. It's fundamentally rewiring its own internal architecture to be faster. And, well, as we'll see, it's hitting some really fascinating hard limits when it comes to human-level software design.
Yeah, and the real story hidden in all this new data isn't just about developers building bigger and bigger models. I mean, we've seen that.
Right.
The story is about building smarter, physically grounded models.
Yeah.
Models that actually understand the friction, the gravity, and the chaos of the environment they're operating in.
Okay, let's unpack this. Starting with the most visceral change, which is AI escaping the screen. Genesis AI just dropped a new foundation model called Gene 26.5.
Which is essentially a new brain specifically for robots.
Right. Pushing them toward human-level dexterity. And the examples are just wild. We're talking about a robotic hand cracking an egg with one hand.
Yeah, which is impressive.
Which, let's be honest, half of us humans still struggle to do without, getting shells in the pan.
Oh, absolutely. And it doesn't stop at the kitchen either.
Mhm.
This model is it's operating highly precise lab pipettes and even autonomously solving a Rubik's Cube.
Wow!
Yeah, manipulating it in all dimensions.
Which, I mean, that sounds cool on a YouTube video, but I think we really need to conceptualize how insanely difficult this is. It's like trying to tie your shoelaces while wearing thick winter mittens in the dark.
That's a great analogy.
We completely take for granted how our hands instantly adjust pressure when, say, an egg slips just a millimeter.
Yeah, and what's fascinating here is the sheer mathematical complexity of that slip. Because, robots have always been exceptional at repetitive factory tasks, right?
Right, like car assembly lines.
Exactly. A robotic arm on an assembly line moves to the exact same coordinate thousands of times a day because the environment is perfectly controlled. But the real world isn't controlled.
No, not at all.
When an egg slips, the robot has to instantly calculate the new center of gravity, the fragility of the shell, the required counter pressure, all in milliseconds. So giving an AI the ability to adapt autonomously to those tiny, unpredictable variations, I mean, it expands what they can do exponentially.
And then, LabOS is taking that physical awareness and merging it directly with human workflow.
Yes, the AI co-scientist.
Yeah, this AI co-scientist system that uses extended reality, or XR, smart glasses. So it actually watches human scientists perform physical lab experiments. It's not just reading data off a screen anymore.
Right, it's tracking subtle physical movements, like the angle of a researcher's hand, or even the rhythm of how they're pipetting a liquid.
Which is crazy.
It is, because it acts as an active physical spotter. It holds the entire experimental protocol in its memory, and it understands the spatial dimensions of the lab bench.
Right.
So the XR glasses will visually warn the human scientist before they make a physical mistake.
Wait, really? Before they make it?
Yeah. If you reach for the wrong beaker, it flags it right in your field of vision. It totally bridges the gap between digital knowledge and physical execution.
But, I mean, acting in the physical world requires unbelievable reaction speed. And there's this open robotics foundation model from LNAI called MomoAct2.
Oh, yeah. The speed on that is incredible.
They trained it on 700 hours of bimanual tasks, tasks needing two hands, like folding towels or scanning groceries. And the craziest part is they reduced its action call time from 6,700 milliseconds down to just 180 milliseconds.
And that reduction, I mean, that is the difference between surviving an environment and completely failing in it.
How so?
Well, think about the last time you knocked over a glass of water. Your brain processed the visual of the falling glass. It calculated its trajectory, and it fired a signal to your arm to catch it, all in a fraction of a second.
Right.
If you had a nearly 7-second delay, which is essentially what 6,700 milliseconds is.
The glass is already shattered on the floor.
Exactly. 180 milliseconds brings the AI down to human reflex speed.
And to train that kind of spatial awareness, I mean, you can't just have robots breaking millions of actual eggs in a physical lab, right?
No, it would cost an absolute fortune.
So researchers are using an AI called PhysForge, which it creates 3D virtual assets that have actual physical properties. So they aren't just drawing a 3D block on a screen.
Right. They are coding the actual gravity, the mass, the friction into the block.
Yeah. So the AI experiences the realistic weight of it.
It gives robots a highly accurate virtual playground. The simulator calculates how, say, a material would slip, or how it would weigh down the robotic arm's joints.
So they master the physics of our world virtually.
Yeah, so they don't break things when they finally touch reality.
Speaking of joints, Boston Dynamics just showed off their fully electric Atlas humanoid robot. And it's doing headstands, but then it rotates its joints 180 degrees.
Oh, I saw that. It's wild.
It's literally exceeding human biology. To turn around, it doesn't like step its feet in a circle. It just rotates its torso backwards while standing completely still.
Yeah, it looks a bit unnerving, to be honest, but mechanically it's incredibly efficient. I mean, human joints are constrained by ligaments and bone structure. A robot doesn't have to be.
Right.
We're starting to see AI figure out that it doesn't need to mimic human movement perfectly, if it can find a more efficient mechanical shortcut.
Though, I mean, they still have some balancing to learn, right? There was a robot fight recently between the Unitree G1 and the Engine AI PM1.
Oh, the King Fu kicks?
Yes. They're throwing kung fu kicks at each other, and it ended in a double knockout where they both just fell over.
Yeah, because navigating gravity is still a formidable physics problem. When you throw a kick, your center of mass shifts dramatically.
Right, obviously.
So the AI has to calculate dynamic balance in real time just to keep the robot upright. And when two robots collide, that map gets thrown into utter chaos.
Right.
So the easiest resolution for the system is to just...
let gravity win.
Exactly. Just fall over.
But, surviving that physical chaos or catching that falling glass like we talked about, it requires a fundamental shift in how the AI brain actually operates.
It really does.
Because to react in 180 milliseconds, the AI cannot afford a processing bottleneck. So we're seeing this efficiency revolution, right?
Yeah, the industry is shifting away from just throwing raw brute force computing power at a problem.
Right.
And moving toward incredibly clever memory management. Because the bottleneck isn't actually how fast the processor can think.
Wait, it's not.
No, the processor is incredibly fast. The delay comes from the time it takes to move billions of parameters, basically the AI's knowledge, out of the computer's memory and into the processor just to generate a single word or action.
Oh, wow.
Yeah, the processor is essentially sitting there twiddling its thumbs, just waiting for the memory to catch up.
Okay, here's where it gets really interesting, though, because Google just upgraded their open source model, Gemma 4, using a brilliant workaround for this memory problem called speculative decoding. So they paired the massive Gemma 4 model with a tiny, lightweight drafter model. And this tiny model, it runs ahead and guesses several words or tokens in advance.
And if it guesses correctly, the big model accepts them instantly.
Right. It sped Gemma up by 3.1 times, hitting 80 tokens per second. But let me push back on this for a second.
Sure.
If this tiny, less capable model is out there just guessing the end of the sentence to save time, doesn't the AI hallucinate more or just get sloppy? I mean, is it like a sous chef chopping all the vegetables so the head chef can just cook the meal instantly? But what if the sous chef chops the wrong vegetables?
That's a really good question, but the output quality stays exactly the same.
Really? Zero downgrade?
Zero downgrade in reasoning.
Yeah.
And the reason your sous chef analogy actually holds up perfectly is because the larger head chef model acts as the ultimate instantaneous quality control judge.
Oh, I see.
Yeah, the big model is reviewing the tiny model's homework in real time. If the tiny drafter model guesses the wrong word, the large model simply rejects it. It throws out those chopped vegetables and computes the correct word itself.
Okay, so you lose a microscopic fraction of time checking.
Right. But when the drafter guesses right, which it often does for predictable grammar, you skip massive amounts of data transfer.
Wow. But speculative decoding is just a clever software trick, right? What if you fundamentally redesign the model so it doesn't blow out its memory to begin with?
Now you're talking about structural changes.
Exactly. And that brings us to Zaira's new model, Zaya 18B. It's an 8 billion parameter model, which is tiny in AI terms, but it's punching wildly above its weight. It's competing with massive 235 billion parameter
It really
models.
is.
And it has two massive firsts. First, it was trained entirely on AMD hardware. It's breaking the absolute reliance on NVIDIA chips.
Which, I mean, that signals a massive structural shift for the tech industry's supply chain. The monopoly on AI compute is finally fracturing.
Yeah. And the second breakthrough is how it thinks. It uses a method called Markovian RSA.
Right.
So instead of just generating one long, rambling chain of thought, the AI generates multiple reasoning attempts, picks the absolute best pieces of logic, and only passes those successful pieces forward to the next round of thinking.
And that solves one of the biggest problems in AI right now, which is blowing out the context window.
The context window.
Yeah, think of a context window as the AI's short-term memory, like a whiteboard.
Okay.
When an AI tries to solve a complex math problem, it writes out all its steps on this whiteboard. If it gets lost halfway through, it just keeps writing bad logic, filling up the whiteboard with garbage until it's completely confused.
Oh, so it just overloads itself.
Exactly. But Markovian RSA changes that. The AI writes out, say, 5 possible first steps, evaluates them, wipes the 4 bad ones off the whiteboard entirely.
And only keeps the correct step to build upon.
You got it. It keeps the model's memory perfectly clean and lean.
And we're seeing this push to cut wasted effort everywhere. Like Sakana AI partnered with NVIDIA to introduce sparse math for transformers.
Oh, the tilewise LPAC.
Yeah. They realized that inside an AI's brain, a massive percentage of the calculations it's doing are essentially just multiplying by 0.
Which is completely wasted processor energy.
Exactly. So they developed this new format, tilewise LPAC. It basically acts like a filter, allowing the processor to completely ignore empty data packets instead of calculating them. And it yielded 30% speedups and 30% energy savings.
And if we connect this to the bigger picture, solving this energy and memory crisis is really the only way this technology actually scales to consumer devices.
Because you can't put a liquid-cooled server farm inside a smartphone.
Exactly. You have to make the model capable of skipping wasted work so it can run locally on your devices without draining the battery in like 10 minutes.
And the real-world application of this speed is just jaw-dropping. OpenAI just dropped their GPT real-time translate model. It translates spoken languages instantly.
It's amazing to see in action.
But the wild part is, if you are translating from, say, German to English, the AI literally waits for the speaker to drop the verb at the end of the German sentence before it perfectly shifts the language.
Right.
It understands the grammatical structure and pauses naturally without missing a beat.
And to process incoming audio, hold the context, wait for the verb, translate the grammar, and synthesize a natural human voice all in a fraction of a second.
Yeah.
That is only possible because of the underlying efficiency revolution we just walked through. The AI isn't bogged down moving irrelevant data. It's lean enough to operate at the speed of human conversation.
So what does this all mean? We have AI that is fast enough to translate real-time speech, it's smart enough to physically spot a scientist in a lab, and it's efficient enough to run on local hardware.
Right.
But when we ask these hyper-advanced AIs to just sit at a computer and design a system from scratch, we run into a fascinating paradox.
We really do. We are hitting the hard boundary line of current artificial intelligence.
Yeah.
It's the paradox of incredible self-evolution versus total systemic failure.
Okay, let's start with the triumph side of it, because it honestly sounds like science fiction. Google has an AI called Alpha Evolve, and its entire purpose is to discover better algorithms.
Yeah.
And over the last few months, it has become an automated invention machine. It improved deep consensus DNA sequencing error detection by 30%. It jumped power grid optimization from finding feasible solutions 14% of the time to over 88% of the time.
And that power grid metric, I mean, that isn't just a number. It is fundamentally changing how electricity is distributed.
How so?
Well, a human engineer simply cannot map out the millions of dynamic permutations required to balance fluctuating wind and solar loads across a national grid in real time. Alpha Evolve found routing efficiencies that humans just couldn't see.
Wow.
Yeah, which translates to a drastically smarter, more reliable energy grid.
It also reduced quantum circuit errors by 10x, but the wildest achievement. Alpha Evolve is currently designing the next generation of Google's own TPUs. They're AI microchips.
Yeah.
The AI is literally inventing better hardware for itself.
It is the definition of a self-improving loop. It tests a chip layout, evolves a better pathway for data to travel, and iterates millions of times at a speed human engineers simply cannot match.
So keep that in mind, for everyone listening. This AI is designing quantum circuits and AI microchips. But now look at the total failure side of the paradox. There's a new stress test called Program Bench.
This one is brutal.
It really is. In this benchmark, an AI is given a finished, compiled, executable file dash, like a .exe file on your computer dash and the program's documentation. It has no access to the source code, no internet, and it can't decompile the file.
Right.
Its goal is to reverse engineer and write the entire software from scratch. It has to be the software architect.
It has to run the program, observe its behaviors, choose the programming language, design the file structure, build the database architecture, and then write the full code base.
And out of 200 tasks ranging from simple command line tools to complex databases like Sucklite, the top models in the world, including Opus 4.7, GPT 5.4, and Gemini 3.1 Pro, scored exactly 0% success.
Wow.
Opus managed a meager 3% partial resolution. None of them could rebuild a basic piece of software. So I just have to ask, how can an AI be smart enough to invent a better quantum physics circuit, but completely fail to rebuild a basic software program?
Right. Well, if we connect this to the bigger picture, it breaks down the fundamental difference between optimization and architectural vision.
Okay.
Alpha Evolve is an optimizer. You give it an existing set of boundaries, a defined problem like a microchip layout, and it iterates millions of times to find a 5% or 30% optimization. It's incredibly powerful, but the sandbox is already built.
Ah, I see. So it's tweaking the dials on a machine that already exists.
Exactly.
Yeah.
Program Bench, on the other hand, requires 0 to 1 human design. It requires making structural choices, anticipating how 1,000 different pieces of code will interact down the line, testing abstract behaviors, and holding the grand, interconnected blueprint of a project in its mind.
Right.
AI is fantastic at writing code snippets. It's autocomplete on steroids. But it completely lacks the big-picture architectural vision required to build complex systems from scratch.
It's like hiring a master bricklayer who can lay a perfectly level, optimized wall faster than anyone on Earth. But if you ask them to draw the blueprints for an entire skyscraper, the building collapses.
Yeah.
They understand the bricks, but they don't understand the building.
That's a great way to put it. And that's why Program Bench is such a brutal but completely necessary reality check. We can get AIs to write a Python script or fix a bug in seconds, but acting as a true software architect requires a much deeper cognitive leap that these models just haven't made yet.
So to synthesize everything we've covered today for you listening, we are watching a massive paradigm shift. AI is no longer just a text generator trapped behind glass. It is becoming physically grounded.
Using models like Gene 26.5 and simulators like PhysForge.
Right, to understand the chaotic physics of our world. And it's undergoing an efficiency revolution using tricks like speculative decoding and tile-wise LPAC filters to bypass memory bottlenecks.
So it can process information fast enough to actually survive in that physical world in real time.
Exactly. And while it is starting to invent its own highly optimized algorithms, we can rest easy knowing it still lacks the 0 to 1 architectural vision of a human engineer. You are now equipped with the actual frontier of this technology, cutting right through all the hype.
It's a rapidly shifting frontier, though, and I think there's a really vital question to leave you with today as you digest all of this. We saw that Google's Alpha Evolve is currently designing the next generation of AI chips. It is actively making the physical hardware more efficient.
Right.
If the AI is already engineering the silicon that will be used to train the next generation of AI, at what point does human engineering stop being the driving force and start becoming the bottleneck in that loop?